Hello, this is Rick from MathX, and today I'll be doing something a little different than usual. Usually on this channel, we go over a hard math problem from a prestigious competition, and I explain you every bit of the solution. However, today I would like to explain a concept that is useful for attacking lots of these competition problems. Combinations and permutations. Now, I said a concept, but I listed two concepts. Well, that's because combinations and permutations are tied indirectly with each other. So if you understand one well enough, you'll understand the other. These concepts are very fundamental if you want to do good on higher level competitions and even the basics. These concepts are added onto each other to make way for you to understand more advanced concepts in counting. So without further ado, let's get straight into learning about combinations and permutations. The first thing you need to know to understand how combinations and permutations work is the special notation called factorial. When you find the factorial of any number n, you'd express it as n and then this exclamation mark after it. And this basically represents the product of all the numbers from 1 to n. So n times n minus 1 times n minus 2 all the way to 1. So what does this mean for finding like a number like 3 factorial? Well, 3 factorial would be equal to 3 times 2 times 1. So it's equal to 6. Another number would be 5 factorial. That's just the same as 5 times 4 times 3 times 2 times 1. Multiplying it up, we would get 120. However, most of the time we don't need to compute 5 factorial by just multiplying all the consecutive integers up. Because using factorials, we can make operations a lot quicker, especially division. When we want to divide a larger factorial by a smaller factorial, well, we can use an interesting trick. Let's do something scary. Let's try to divide 99 factorial from 100 factorial. Now, 100 factorial is the product of all the numbers from 1 to 100 inclusive. And 99 factorial is the same thing, but with 99. Both of these numbers are incomprehensibly huge, so it's going to be impossible to calculate each of them independently. However, there's one thing we can note. 99 factorial will appear in 100 factorial because 100 factorial is just 100 times 99 times 98 times 97 all the way to 1. 98 factorial is just 99 times 98 times 97 all the way to 1. So the 99 factorial will appear in this 100 factorial. And the only number left after the 99 would be 100. So this number could be written as 100 times 99 factorial over 99 factorial. We can just cancel out the 99 factorial, getting 100. So in the end, we made this incomprehensible operation much simpler by just acknowledging that 99 factorial already existed inside the 100 factorial, and that there's only an extra 100 in this case. So basically that's factorial. Factorial is the product of all the numbers n to 1, and we can use division quite easily with factorial, as factorials of smaller numbers can be found in factorials of larger numbers, allowing us to cancel them out and be left with only the numbers greater than the largest number in the factorial below. Now, what does this have to do with permutations? Well, permutation describes the number of ways we could arrange a set of objects with regard to order. Well, what does that mean? I just listed out a bunch of fancy jargon. Well, basically what a permutation comes down to is a question like how many ways could we rearrange the letters in the word dog? Or how many ways could we rearrange the letters in the word cat? Or how many ways could we rearrange a set of balls? It comes down to rearranging stuff. And the second part, with regard to order, well, that means different orders are distinct from one another. So when in the case of rearranging the word dog, DOG is different from DGO or GOD or GDO. These are all different from one another. So their position relatively to each other is distinct. Now, speaking of this permutation problem, what would be the answer to a problem like this? Now, with these kinds of permutation problems, honestly, the best way to attack this is just using logic. Dog is a three-letter word. That means that there's three places to put letters in. How many letters could go in the first place? Well, there's only three letters. D-O-G. That means there could be three different letters in the first place. In the second place, well, we already used one of the letters, whether it be D, O, or G. We already used one of the letters. So in the second place, there can only be two letters. In the final place, we already used two letters. So no matter what two letters we've already used, there's only one letter left. So it comes down to 3 times 2 times 1. Where does that look familiar? Oh, wait. That's just 3 factorial. So the number of ways to rearrange the letters in the word dog is just 3 factorial. What about in the word cat? Well, I'm not going to write anything because if you look at it, cat and dog are pretty similar, even though they're as different as dog and cat. In the first spot, for cat, there could be 3 different letters, so 3. In the second spot, we already used one letter, so there's only 2 letters left to put in the second spot. And in the final spot, we already used 2 letters, so there's only 1 spot left. Once again, cat also has 3 factorial different ways to rearrange the letters in the word cat. So this is pretty useful. We can easily find a way to rearrange distinct terms with one another. However, what if all these terms were not distinct? What if it was a word like book? We can't simply say that book is just 4 factorial, because that would be treating these O's differently. And even though I may have drew them a little differently, O is O. There's nothing special about this O versus this O. These two O's are the same. B-O-O-K, with this O being first and this O being second. That's the same thing as having this O first and this O second. So, in order to find the number of ways we could rearrange the letters in the word book, we have to do some overcounting and then get rid of the extra terms. So, if both of these O's were distinct, there would be 4 times 3 times 2 times 1 different ways to rearrange the letters in the word book. Because we use a similar strategy as we used here. We see that in the first spot, we could have any of these 4 letters in the case where I'm treating O as distinct. Second case, well, we already used 1, so there's 3 left. We already used 2, so in the third spot there's 2 left. And then in the final spot we already used 3, so there's 1 left. So there would be 4 factorial ways. But that's treating the O's distinct. So in order to cancel that effect out, we just need to find out the number of ways that we could rearrange these O's, and then we just divide that, because each of these cases would be counted the number of ways we could rearrange the number of O's times. So in this case, we could rearrange these O's in 2 factorial different ways. So 2 different places for the first O and 1 different place for the second O. So 2 factorial different ways we could rearrange these O's in a sequence. We have to divide it from the initial numbers of ways to rearrange the letters B, O, O, K in the sequence. So that gives us 4 factorial divided by 2 factorial. Remember the trick we learned earlier. We can just get rid of the 2 factorial from the bottom and top, because 2 factorial also appears in the top. So if we do that, we're just left with 4 times 3. 4 times 3 is just 12, giving us 12 ways to rearrange the letters in the word book. But all these cases I've been using so far are only regarding letters and rearrangements of words. Surely these are not the only types of permutation questions, and you're right. So I'm going to give an example of a word problem. So let's say we have 8 kids, and we want to create a competition for them. They could come in either first, second, or third place. How many ways could we assign each kid to first, second, or third place? Well, we use a similar kind of idea as what we've been using before. In the first place, there could be 8 different kids. In the second place, we can't put 8 different kids because one kid's already in first. We can't have a kid be in first and second place at the same time. So instead of having 8, we're going to have 7. And then for the third place, we already used 2 kids in first and second place, so there's 6 different places. Now, this looks kind of different from what we've been using before. All our expressions and values in the past have been in regards to factorial, but this doesn't seem to have any factorial. Sure, we have multiplication of consecutive terms, but it doesn't seem to be factorial. So this is where I'll bring in the formal expression to find the number of permutations for a value. Up until this point, we've been computing it using just logic, but there's an actual formula to compute the number of permutations in an object. The formula looks like this, NPR. And this basically means n factorial over n minus r factorial, where n is the total number of objects there are, and r is basically the number of objects you pick. So what does this mean in terms of kids? Well, n is the 8 kids. There are 8 kids, and you want to pick 3 of them to be in first, third, second, and third place. So we would get 8 factorial over 8 minus 3 factorial. Now 8 minus 3 is 5, so it's 8 factorial over 5 factorial. So then, using the trick I've demonstrated above, we can just get rid of the 5 factorial from the bottom and top, and we're just left with 8 times 7 times 6. And wait, that's our answer from above. We used just common sense to attain this answer. We could have also used the formal definition and the formal equation to calculate the number of permutations in the thing. So, as you can see, the factorials are still present in this case. It's just that they cancel out. So we're not then needed once again. So this kind of expression just tells us that permutations is just multiplying numbers in this kind of order. There's n different things for the first spot, n minus 1 different things for the second spot, n minus 2 different things for the third spot. And we keep on doing this until we get to r spots. So that's how permutations work. Permutations are just the number of ways to rearrange things. And you always have to remember, since we're rearranging things, order matters. Now on to combinations. Combinations describes the number of ways we could choose a set of objects from a total group of objects without regard for order. Well, what does this mean? This means that we don't care about the order of what we pick anymore. So an example of a question would be like, how many ways are there to choose 2 letters from the alphabet? In this case, we can use common sense again. We have 26 different ways to pick the first letter, and then 25 different ways to pick the second letter, because there's 26 letters in the alphabet. And after we pick the first one, we're only left with 25. However, this would take account for cases like if we had A and B, or B and A. In the case of choose, we don't really care what order we get them in. We don't care if we get an A or B or A. We just want to know how many different pairs of 2 we could get, like whether it be AB or AC. We don't really care about what order they come in. So then, in order to make up for that, we would have to divide by the number of ways that these 2 letters could come to us. So since there's only 2 letters, they could come to us in 2 factorial ways. So it's 26 times 25 divided by 2 factorial. And we can compute this to get 13 times 25, which quick computation will just tell us that's 325. Now, another example of a problem like this would be if we had like a jar of balls. In this jar of balls, let's say we had like different colored balls. We had a red one, we have a green one, we have a blue one, and we have a pink one. If we have 5 different colored balls and we're asked to find out how many ways could we pick 2 different balls, well, once again, we're left with 2 spots. In the first spot, there could be 5 different colored balls. Second spot, we already picked out 1 from the jar, so we only have 4 left. So 4 different. However, let's say we got a pink ball and then a red ball. That's the same thing as getting a red ball and then a pink ball. In this case, order doesn't matter to us. So we'd have to divide by 2 factorial. So we get 5 times 4 divided by 2 factorial. 20 divided by 2, giving us 10. And this kind of gives you an idea on how choose works. Unlike the other case where we just multiply it all out, this case we just get rid of all the different ways we could rearrange them. So when we write out the formal equation, note that when NPR, we got n factorial over n minus r factorial. In this case, we get n choose r to be n factorial divided by n minus r factorial times r factorial. Because remember, in all these cases, we just divided by the number of ways we could rearrange the things we got. So with the letters in the alphabet, there are 2 different orders we could have got them in. So we divided by those 2 factorial different orders. Same thing with the balls, 2 factorial different orders. So we divided by the 2 factorial different orders. In the case of combinations, order does not matter. And we just get rid of it because it gives us extra cases. So before I just move on from combinations, I just like to give one more problem. And then we'll wrap everything up. Let's say we have a company of 12 people. 5 men and 7 females. How many ways can we form a committee of 4 people if there has to be 2 men and 2 females? To solve this kind of problem, we use the choose that we've been acquainted with. Because, remember, if we get like 2 men, Bob and Joe, it doesn't matter what order they come on the committee. It doesn't matter where Bob comes first or Joe comes first. From each of these sets, we have to choose 2 people. So from the man side, we do 5 choose 2. And from the female side, we do 7 choose 2. And since these 2 cases are independent from one another, we just multiply these 2 up. We plug it into the formula. 5 factorial divided by 3 factorial times 2 factorial times 7 factorial divided by 7 minus 2 factorial, which is 5 factorial, times 2 factorial. Now, remember, this is really saving our butts here. We can just divide the 5 factorial out from both sides and the 3 factorial out from both sides. So we do that, we're left with 5 times 4 over 2 factorial and 7 times 6 over 2 factorial. So 5 times 4 over 2 factorial would give us 10. And then 7 times 6 over 2 factorial would give us 21. So there's 210 different ways to pick a committee of 4 people from these 2 groups. So as you can see, combinations and permutations are 2 very important concepts. And today I've just listed a couple examples of how these problems could be used and their differences. But each of these problems can be used in a wide variety of many other ways. But if there's a couple of takeaways I want you to take away from this video, remember, permutations we're rearranging and orders are important. In combinations, we're just picking different groups. Order doesn't matter. And together with these two concepts, just by mastering these two concepts, you can solve a wide variety of problems. So if you want some extra practice or extra experience for how to do permutation and combination problems, I'll put several videos in the links of me solving other hard combination and permutation problems with use of factorial or not. So thank you for watching, and I hope you learned something about permutations and combinations.